Okay, good morning. Welcome to class. So we're going to keep talking about chapter 7 today, but a couple announcements before we get going. On Monday, we're going to review chapter 7 and then we'll take our quiz during our asynchronous session. Probably. That's like what we should be doing. So we'll see how far we get today, and we'll see if we actually get there. Basically, all we have to really accomplish before the end of chapter 7 is electron configurations and photoelectron spectroscopy. So those are like our two big things. We also kind of take this opportunity to go through like the general groups on the periodic table. But that's just more for like background knowledge. So you have some foundation of background knowledge on elements and element groups before we move forward. It's not actually like a hugely testable subject. So that's the goal right now, but we'll see how far we get today and then tomorrow. And then also for tomorrow is kind of an interesting day. Here's what I think we're going to try to do. We're going to try to go through the photoelectron spectroscopy POGL in groups. Now, I'm not 100% sure that I will be able to connect to internet tomorrow. So I'm going to try to set up Zoom so that you guys can do this POGL in groups, in like breakout room groups. But if for some reason I can't connect to internet tomorrow, then the plan is just to do the POGL. So let me show you which one it is. Let's see here. Wait for it. Here we go. Okay, so it's in the packet that has the mass spec stuff on the front, and it's the very last one here, photoelectron spectroscopy. So what this packet talks about is like a type of analysis that allows us to determine the oh my gosh, what's the word I'm looking for? Not the orbital diagram. Oh my goodness. Basically the orbital diagram. The electron configuration. There we go. It's a system of analysis that helps us determine the electron configuration from a machine, like analyzing a substance. We can write the electron configurations for various elements, but what we're writing is like a theoretical. This is based on everything we know. This is probably what the electron configuration is. But this is actually an analysis that will allow us to verify the configuration and support it with evidence. So that's the plan for tomorrow. I'm going to post the POGL on Classroom, which you already have. I'm also going to post the key on Classroom, and then I'll post it again in the resources page so you have it in both places. And then again, I'm going to try to get on to the internet tomorrow so that I can put you in breakout rooms. But if for some reason I can't connect, then just do the packet. I'll probably post like an intro video to it, basically saying what I just said. And then again, if you can do it in conversation with people, you're going to understand it better coming out of it than if you do it on your own. Okay, so questions before we get going in on the warm-up?
you tell us again what chapter 7 questions we were supposed to do? Because I think in Zoom you told us something different than what the assignment says.
It's on Classroom. So if you click on like Tuesday, click on Tuesday. And it's right here on Classroom. And I'll put it again in like the Wednesday material when I post like this video and stuff on Classroom. I'll put it there too. It'll just be a repeat of Tuesday. Does that help, Callie?
Yeah.
Okay. Other questions? Thank you for asking that and clarifying that, Callie. Okay, one last thing. I think I found a better forum page for us. So I've been talking to a bunch of people because I think the real limitation of this class right now is getting enough time with each other so that you can actually get your questions answered. I also think by being online, we're losing a little bit of like the support, the like morale support that usually this class comes with, unfortunately. So I don't know how to fix that. But I'm brainstorming and we're problem solving and I'm talking to lots of people to try to get ideas. So I've invited you all to this thing. It's just another app in your little waffle over here. It's just another Google app. It's called Google Chat. So you don't have to create another account. You're already connected to it. You just have to like join. And then I'm not sure if you guys can post topics, but I'll just post a topic for every chapter, and then we can kind of deal with questions on there. And if a chapter has lots of questions, I'll start posting like individual question topics. And maybe that will give you guys an opportunity to get just a little bit more help answering some of these questions. So there's a section for lab questions. That would be a good place if you still have questions on lab to type your question in. And then we can anyone can answer it. So feel free to answer each other's questions. All right. Here we go. Chapter 7 continued. And this is the warm-up. So go ahead and type your answers in, and let's see how you do. Ooh, you guys are doing so nice. You are right that the fourth shell, also known as the fourth energy level, so shell and energy level mean the same thing, has 4 subshells, S, P, D, and F. So the fourth energy level has all 4 shapes, S, P, D, and F. So how many orbitals are in each of these subshells? That's the last thing to answer. Nice. Yes, S has one orbital, which can hold 2 electrons. P has 3 orbitals, or 3 orientations of the orbital. So 3 orbitals can hold 6 electrons. D has 5 orbitals, so can hold 10 electrons. F has 7 orbitals, so can hold 14 electrons. Okay, I'm going to give you 30 seconds to type in a question that you have on this stuff. Or say the question. Either one. Okay, a couple good questions here. So, what is the meaning of N? N is if you were going to tell me what energy level you're in, or sometimes we refer to that as what shell are you in, that's N. So if I say N is 3, that means you're in the 3rd energy level, or you are talking about the entire 3rd shell. That's what N is. And then L would be referring to the shape or the subshell, like 4S would contain N and L, and that'd be a subshell. And then M sub L tells you the orientation. So if you have N, L, and M sub L, like 4px, that would be 1 orbital. Okay, another good question. Are orbitals and energy levels the same thing? And the answer is no, they are not. So let me give you an example of this by drawing it. If I was going to draw, let's just do the 2nd energy level because that is a lot less complicated than the 4th energy level. So if I'm going to draw the entire 2nd energy level, N equals 2, I would draw this. So well, let me start over. Okay, I would draw 2s, 2px, 2py, 2pz. So these are areas where I am likely to find an electron, right? And these are all the areas in the 2nd energy level where I am likely to find an electron. That would be an energy level. A 1 complete energy level described by N equals 2. If I'm talking about 1 orbital, I'm talking about a specific energy level, specific shape, specific orientation. So 1 orbital would be like 2px. 2px equals 1 orbital, which can hold 2 electrons. So if you're talking about an electron or an orbital, you're talking about an area of space that can be occupied by at a maximum 2 electrons. Okay, so the M sub L is how many orientations, or orbitals each subshell has. Yes, that is a correct statement. The M sub L is how many orbitals each subshell has. Yes. L is shape, M sub L is orientation. SPDF are subshells if you give them a specific energy level. So like 2P, 2S, 3D, those are subshells. Yeah. And N is energy level. Yes. Good. Good processing, y'all. Okay, I don't see any other questions. Oh, one more. When it gives us just N, when do we know it's 4S or 4P? You don't. If they tell you you're in the fourth energy level, then you don't necessarily know which shape you're in or which subshell you're in. So if they say n equals 4, that's referring to all the shapes. So if your question is, how do I know which shapes n equals 4? That goes back to yesterday's notes. So remember, n is size, L is shape. So what you're really asking are, what are the possible L's? And remember, possible L's are everything from 0 to n minus 1. So if n is 4, I can have 0, 1, 2, or 3, because n minus 1 is 3, which means I have S, P, D, and F. So you got to go back to those rules from yesterday. If you want to know what possible shells there are, you have to know those rules. Learn those rules. Okay, now I think we've covered all the questions. Good questions, you guys. Oh, one more. So can I assume each 2px, 2py, 2pz holds the same amount of electrons as 2s? Yeah, because they're all one orbital. 2s is an orbital, 2px is one orbital. So 2s would hold 2 electrons. 2px would also hold 2 electrons. Exactly. If you're talking about one specific orbital, they're always and forever just holding 2 electrons. Okay. Good questions, you guys. Oh my gosh, I feel like I'm answering your questions. It's a good feeling. Okay, orbital representations. So there's a couple different representations you might see, and they're all trying to communicate the same thing. I just want you to be aware that you might see them. Okay, so for example, you might see this area of probability known as an orbital as a solid shape. And what they've done is they've just drawn a border around 90% of the probability. You might also see it as like a dotted diagram. And notice if you're talking about the 1s, it just kind of looks like a solid sphere. But if you're talking about anything higher, like the 2s or the 2p, notice that there's little like spaces in between those. Those are nodes. If you have taken physics, you know what a node is. If you've not taken physics, a node is if you have like a wave, if you have a string and you shake the string upside down, the string's going to go up, down, up, down, up, down, right? Well, if you do it super fast, your eyes can't tell the difference between the string when it's up and when it's down. And so basically you get something that looks like this, and this looks like a solid sphere. Even though it's not, it's just a string moving up and down really fast, it still looks like a solid sphere. Well, these areas where the string remains at rest, here and here and here and here and here, those are called nodes. And so a node in terms of electrons would be a location where the electrons don't spend time. And basically it happens because of the interaction of the shells beneath it. Like n equals 1, the 1s sphere is going to be nestled inside the 3s sphere. And the electrons that are in the 1s sphere are going to repel the electrons from the 3s sphere. And so they're going to create this ring. This ring occurs inside, which is an area where electrons don't typically spend time because of that repulsion. You could also see that communicated as a solid. And then what I really want to show you is the graph up above. So this graph is showing you, so it's electron density basically on the side. What you would probably see it labeled as is like electron probability or radial probability, something like that. But basically what they're talking about is where do the electrons spend time. And then on the bottom here, this x-axis is distance from the nucleus. So the nucleus would be like here, and this is going to go to infinity away from the nucleus. Okay, so what you'll see is kind of a graph that's similar to the graph that you saw yesterday when you were playing with those electrons and you like force the electrons together, right? So the electrons have this happy place when you're talking about distance to the nucleus. So if you take the electron and you move it too far away from the nucleus, it is going to want to attract to the nucleus. So you won't have very many electrons this far, spending time this far away from the nucleus. As you move the electron closer, the potential energy drops, and you get more electrons that spend time here. And then as you move the electron even closer, you're going to get repulsion that occurs because the electrons don't like to be too close to the nucleus either. And so you get this like happy medium in here. And then if you look at like the other spikes, like this green one, that would be like a 3S chart. And then these dips, again, they represent the nodes that occurs because of the repulsion between the 3s electrons and the 1s electrons. All right. So just wanted to show you a couple different like views that you might see these orbitals like described with. They're all trying to describe the same area of probability where we are likely to find the electron. All right, and then here is a shape. Here are the various shapes that you might see. So here you can see this is the S shape. Here we have X, Y, and then I'm assuming this is like this is 3D. Okay, so you can see like the dumbbell shape. You can see a very typical clover shape here. And then here we start getting kind of more electrons interacting. So we get a couple D shapes that are fairly unusual. And then the F shapes are kind of all over the map. This is why we just call them crazy. It's not even worth trying to describe them. And then you can see some of the higher orbitals. The shells start to get a little bit less describable because we're having that interaction, which is pushing electrons into different shapes. So really what you have to know is like S is a sphere, P is a dumbbell, D is a clover, and you really don't have to know beyond that. But I don't want you to get into like your chemistry doctorate and be like, Mrs. Martin's lied to me, right? Okay, other shapes exist. They're just beyond the scope of our class. And you really don't have to be able to deal with them or describe them or anything like that. Just be able to describe and deal with the basic stuff. Okay. Z effective nuclear charge. So when we start talking about the periodic trends, which hopefully we will get to talk about either today or maybe I'll go through them in the video tonight. This Z effective charge is an important concept for you to be able to wrap your brain around. I think we talked about it a little bit in chemistry, but I don't think we put a huge emphasis on it. And basically the idea is that when you look at a valence electron, it's not necessarily experiencing the whole charge of the nucleus. So let me walk you through the concept and then we'll apply the concept when we talk about some of those periodic trends. So for example, let's do lithium because lithium's pretty simple. So lithium has a nucleus of a 3 plus, right? 3 protons in the nucleus. So its nuclear charge is 3 plus. So that is Z. Z is its nuclear charge. So if we're doing this in terms of lithium, this would be a 3. Now, lithium has 3 electrons, and they are going to be 2 in the first shell and then 1 in that final shell. So these inner or core electrons, they are going to feel an attraction of 3+ to that nucleus. So those electrons are actually going to be drawn closer than the one electron in hydrogen, because hydrogen, for comparison, just has a nuclear charge of 1. So the core electrons in lithium will be drawn closer to the nucleus than that core electron in hydrogen would be, because of the higher nuclear charge. However, if we look at this valence electron of lithium, right? The valence electron of lithium is A, farther away from the nucleus just because it's repelled by those core electrons, and B, the nuclear charge is blocked. These electrons are blocking the nuclear charge. They are in between that valence electron and the nuclear charge. And so this outermost electron, this valence electron of lithium, isn't going to feel a nuclear charge of 3. It's going to be reduced. That nuclear charge it feels is going to be reduced by these core electrons, which we call shielding electrons. They act as like a shield in between the outermost electron and the core. So we have 2 shielding electrons in lithium. And so our effective nuclear charge, the nuclear charge that the valence electron effectively feels or actually feels, is 1. So that outermost electron of lithium actually feels the same nuclear charge as the outermost electron in hydrogen, but it's farther away. And so this has all sorts of implications for reactivity and atomic size and ion formation and these kind of things. Okay, so that's the concept behind effective nuclear charge. So why don't you guys figure out what is the Z effective for fluorine? Let's go to the other side of energy level 2. We just did lithium, right? Let's now do fluorine. Fluorine, figure out for me, what is the effective nuclear charge, the Z effective, for a valence electron of fluorine? I'll give you 30 seconds. Type it into Pear Deck for me, please. Okay, so nuclear charge for fluorine is going to be a 9. It has 9 protons. Core electrons for fluorine is going to be a 2. Again, fluorine is in that second energy level, so it has the same amount of electrons in its first energy level as lithium does. It just has more valence electrons, right? So the Z effective for fluorine is 7. Every single one of fluorine's valence electrons will feel an effective nuclear charge of 7. Questions on that?
So when you get up into like when they have higher than 2 energy levels, so say like chlorine, how do you figure out, is the shielding, the amount of electrons shielding, is it still 2 since those are the ones in the first energy level, or is it higher than that?
Yeah, so good question, Leni. For chlorine, the shielding electrons are anything that's a core electron. So anything that's not a valence electron. So the valence electrons for chlorine would be things in the third energy level, right? So the shielding electrons would be the electrons in the first and second energy levels.
Okay.
Yeah, good question. Other questions to clarify this concept? Okay. So Z effective, as Lainey just pointed out, it's going to increase as we go across the periodic table, because as you go across the periodic table, you're going to be adding protons, right? But you're not adding any core electrons. You're not adding any electrons to the first or second energy levels if you're in the third. But as we go like down the periodic table, Z effective should stay very constant for a family. Now, it does change slightly. I mean, Z effective is a simplified model. So these aren't the only factors that are in play here, but it gives you a pretty good indication of what the force the electron is feeling, which is fairly consistent for a family. And so what ends up also being fairly consistent in one family? Because the Z effective is consistent in a family, which is a column on the periodic table, what else ends up being consistent?
Is it the number of valence electrons?
That is true, yes. The number of valence electrons is consistent. And so what is something we care about very much as a chemist that is also consistent? So we can add that to the list. Z effective is consistent. Valence electrons are consistent. Therefore, the whole family I'll give you a hint. It does something consistently that chemists care about very much. Yeah.
Gain electrons?
Cyrus typed it in. It's also going to be, you're right, Luis, it's going to also gain and lose electrons very consistently, which is what reactivity is, right? Yeah. So the whole family has really consistent reactivity, and this Z effective concept is part of that. They're all going to react very similarly, which is good for us. We like predictable things as chemists. Okay, we talked about this slide already. We talked about the electron spin and how this is the fourth quantum number, and it's really only two options, and those two options aren't dependent on any other quantum number. So the two options are plus a half or minus a half, which means electrons can spin up or they can spin down. So when we put electrons into orbitals, like let's say we're talking about the 2p orbitals, electrons can spin up, up, up. As soon as you go to pair an electron into an orbital, the second electron must spin down. And so this is that fourth quantum number. So what you should be able to do for all electrons, if I pick an electron out of an atom, you should be able to write me, this is called the Pauli exclusion principle, by the way. You should be able to write me a series of 4 quantum numbers. So for example, let's do the one valence electron in lithium. The one valence electron of lithium it'd be in the second energy level. It would be in the S shape, which is 0. It would be in the only orientation that it has, and it would be spinning up. So we say these things, we have these things stated, like second energy level, S shape, only orientation spinning up, but we can also quantify that. We can numerically represent that in something like this. And it would be like writing the address of your house. Where do we find Mrs. Martins? Well, we find her in Oregon, in McMinnville, on this specific street, in this specific house. Well, where do we find the valence electron for lithium? N is 2, L is 0, M sub L is 0, M sub S is 1/2. So kind of like this would be the summary of all the slides we've been talking about. So why don't you write me the quantum numbers for the valence electron of aluminum, the one that lives in the P shell. And go. Yes, M sub S will always either be +1/2 or -1/2. Those are the only two options. All right. Quantum numbers for the valence electron of aluminum that lives in the P shell. And if you have a question, instead of typing your answer into Pear Deck, you can just type your question into Pear Deck. Tell me where you get stuck. If you can't answer this, tell me where you get stuck. Callie, I'm going to answer your question on the side. Okay, so here's what we're doing right now. We are writing the 4 quantum numbers for the valence electron of aluminum that lives in the P shell. Francis has a good start here. N is equal to 3, yes. Keep going. Peyton, check your L value. Ooh, nice, Lainey. Nice, Callie. Kaya, check your L value. Okay, let's go through this. Let's go through this together. I see a couple people are just stuck as a whole. Okay, so if I'm talking about the electron for aluminum, the valence electron that lives in the P shell, so aluminum's valence electrons will all be, let me just write this, in the 3rd energy level. Since I specifically said you're talking about the P shell, I want you to use L is equal to 1. If I just said any valence electron of aluminum, you could have used the ones that live in the S shell, so your L would have been 0. but I want you to use the one that lives in the P shell, so your L is equal to 1. M sub L, so if my L value is 1, M sub L can be -1, 0, or 1. And these all just refer to the fact that L has 3 orientations. So you can actually pick any of these values. It doesn't matter. You could put -1 and you would be correct. You could put 0 and you would be correct. You could put 1 and you'd be correct. There's no like rhyme or reason why you would pick one over the other. And it's kind of the same story for M sub S as well. You can say +1/2 here for M sub S, or you can say -1/2 here for M sub S. And there's really no rhyme or reason why you would pick one over the other. So either one would be a correct answer. So this is one possible answer to the question that I asked. Any questions off of that?
So for the M sub S, you said that, is it for any element you can put +1/2 or -1/2, or is it just for aluminum?
No, it's for any element.
Okay.
If I asked you for like, I don't know, sulfur. Okay, if we did the two of the valence electrons for sulfur that are living in the same orbital, one would end in +1/2. The other one would have to end in a -1/2. So that's the only time you're kind of forced into a decision. If you're discussing both electrons in the exact same orbital, they just can't match. But other than that, it really doesn't matter which one you choose. Okay, that's class. It's officially lunchtime. Today, I feel like has been the best lesson so far because you guys asked questions and I answered them, or you guys answered each other's. So I really love that. Let's try and do this more often, shall we? Okay, so I'll post stuff for tomorrow. I will be here during office hours today, and hopefully I will actually be like opening a Zoom for you tomorrow. If not, I'll at least be online answering questions. Okay. Have a good day. Bye, guys. Happy Wednesday.